Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog. Good evening. I'm Yvonne Stapp for Science for the Public, and I welcome you to our program Contemporary Science Issues and Innovations. Tonight we discover what ocean sediments reveal about the history of Earth's climate, among other things. Our distinguished guest is Richard Murray, Professor of Earth and Environment at Boston University. Dr. Murray received his PhD from the University of California, Berkeley in 1991, and he joined the Earth and Environment faculty at Boston University in 1992 and has been instrumental in the progress of marine biogeochemical research ever since. Dr. Murray's research focuses on the analysis of marine sediments for indications of change over long periods of time. Changes in ocean and marine life chemistry, changes in Earth's climate, changes in tectonic processes. All that wealth of information is recorded in marine sediments. He'll tell us about how these sediments are gathered and how scientists analyze the sediments. And since he's contributed significantly to these methods, he's an excellent resource for state-of-the-art analysis. Dr. Murray's expertise is especially appreciated this time because ocean sediment data has been a key resource in climate change research. But he's gone further. Rick Murray is also a committed citizen, serving as Selectman in his seaside community of Scituate, Massachusetts. He's been a major spokesman for communities like his that are forced to make serious preparations for climate change. We're very fortunate to hear from Dr. Murray tonight on both the ocean sediments and the information they provide, and on the impact of climate change on vulnerable communities. It's a great honor to welcome Richard Murray. Welcome, Dr. Murray.
Thank you for inviting me.
Okay, and we'll start right in. This is a very long word, your field. What do you call that, this convergence field?
Well, I guess the phrase of biogeochemistry is laden with prefixes. There's the bio, there's the geo, there's the chemistry, but what's not said is the physics. But what's great about oceanography in general and overall is the integration of all the core fields of science.
So. Right.
And that's what that phrase means. It's no longer possible just to, if we really want to understand how the Earth system works, and something as complicated as climate, or something as complicated as virtually anything now of geology or oceanography, we really need to bring together the chemistry, the physics, the biology, the geology all together.
So it's really a big change in science these days in that field. What can sediments tell us? Why do you look at sediments? Can you give us an idea, ocean sediments?
Sediments, in short, are sort of pages of a book. Mm-hmm. And they record, not always perfectly, but they record overall the history of our planet. And as the sediment is deposited relatively quickly or relatively slowly in the ocean basins, we're able to take marine cores. We go out on ships, we lower basically hollow pipes down to the seafloor, plunge the pipe into the sediment and pull up the core, and we're able to look at either the different geological compositions or the chemical compositions or the biological compositions. And they record Earth's natural system if we go back relatively deep in time, but also if sedimentation is fast enough, we're also able to look at changes only over the last 50 years or 100 years or so.
I remember that we were talking a little while ago, and you mentioned that this varies around the world. You go all over the world getting ocean sediments, but you said it depends on whether they were developed fast or slow and so on. What makes that difference?
Sediment can accumulate and be deposited very fast, and if it's depositing fast, any layering that we do gives a very highly resolved record. It's a very fine-tuned record of short periods of time because the sediment's piling up fast. That's perfect for what we want to do in some situations if we want to see how climate has changed or erosion has changed or some other process has changed over very fast, short periods of time. Other times, though, we want to look deeper into millions of years of records. And there we intentionally go to sediment that's been deposited very slowly. So our coring devices can penetrate deeply, but get a lot of time recorded. And the sedimentation rate, the burial rate, will vary depending on how much biological productivity there is in the water, so how fast dying plankton settle on the seafloor, how close we are to the continents, so how fast erosion is happening, or other processes such as the wind-blown transport of dust from, say, the Sahara Desert or from the Tibetan Plateau out into the ocean. So there's a geological, a biological, and a chemical and physical reasons that contribute to why sediment might be fast or why sediment might be slow, and we need both to understand completely and develop a full record of change, climate change at different parts of our planet.
So this variation is actually, it's very important. You want like an array of these sediments from different regions, but also in terms of this the speed by which they were deposited, I guess, and so
Absolutely.
on. You really do have the pages of a book in that case.
Absolutely.
It's much more comprehensive.
That's right. Just like there's no one book,
Yeah.
you know, in the reference section of a library that can give you all the answers to everything.
Yeah.
Maybe some would say that's Wikipedia, but,
no,
it's
yeah,
not.
right.
We need cores from all over the world.
Okay.
For example, one of the really interesting questions going on in climate studies these days is the role of Antarctica, southernmost continent, deeply buried in ice, and the role of Greenland and the northern hemisphere,
Right.
which has been very well studied. And the relationship between glacial and non-glacial states of climate in Earth history in the northern hemisphere compared to the southern hemisphere. There's no one location you can go to get that. So colleagues of mine or myself, we take a lot of sedimentary records near Antarctica. We take a lot of sedimentary records in the North Atlantic or the North Pacific to try to study this hemispheric contrast. So we need to go all over and get different burial rates, different biological records, different land-derived records, all out in the open ocean to sort of weave that tapestry of Earth's history.
To say it is like you weave it together
Absolutely.
in the end, that it doesn't. It's one area is not representative of the whole planet by
That's
any
correct.
means. So it's much richer than that. What are the most interesting things in a sediment? Does that vary, or like, what do you look for? What is particularly significant?
Well, I think if you asked 100 marine
Oh, it
geologists
gets something different.
what they found was the most interesting part
Yeah.
of mud, we'd probably come up with 200 different answers.
Yeah.
But just like the field title sort of says, there's biology involved. Some of my work with colleagues in particular from the University of Rhode Island is working on the subseafloor biosphere. So that's the biosphere, the microbial ecosystems buried beneath the seafloor. And there we have microbes that have been very slowly as a community turning over because the amount of food down there, basically organic matter that they degrade, is very, very small, way out in the open ocean. So there's a host of people who are studying the biosphere, but to understand the biosphere, we also need to understand the minerals, particularly the iron-bearing minerals or the other minerals that are part of the sediment, because the microbes are living in intimate association with those minerals. So there's the biology and the geology, and there's chemistry involved as well. So that's one sort of area of my personal research and that a lot of people work on. Climate records, some people, and my colleagues and myself, we look at the chemical records of dust that's blowing off of Asia and the Tibetan Plateau, because just like we have a jet stream here in North America that we talk about and we read and we hear about it with the weather and the westerly winds from Asia pick up dust and land-derived material from the Tibetan Plateau, and they blow that out and it lands in the Pacific Ocean. And then I can go out and take marine cores of that. And that gives us an indication in the past of how wet or dry Asia may have been, which tells us about climate.
Right.
And broadly speaking, drier conditions contribute more dust to the ocean, or wetter conditions will lead to a different mineral composition, making it out to the ocean. So we can look at all sorts of different, what we call proxies, because we can't, there's no direct record of climate 5 million years ago.
Right.
We need to make inferences, but our inferences are very well constrained by our studies of the modern. In the last 20 or 30 years, in particular, we have such a better understanding of how our modern system works. So if one parameter is changing, if wind speed is changing, then there's a different record, a different type of dust that's produced in the modern. And so we can then study that and apply what we know about the modern and apply it to the past, which is why we're really able to come up with some quite sophisticated understanding of climate in the past and other processes.
Just before you go on, like with the climate there, you mentioned this, that you can determine where the dust came from.
Yes.
And I'm not sure that we all understand that some of the dust from deserts like the Sahara goes clear across the world and so on. And you're talking about that when it lands in the ocean. You can identify its origins?
Yes, we can. Sometimes in some locations we can do a better or a more precise job than in others. But I've done a lot of work in a small basin just north of Venezuela. And there, it's called the Carioca Basin. And it's a small body of water right next to Venezuela. And there it has very fast sedimentation, like we were just talking about, centimeters per 1,000 years. So it's very, very fast that's fast for us. And so there we're able to look at dust from the Sahara Desert that has blown clear across the Atlantic and ends up getting deposited in this little basin off of Venezuela on its way out to the Gulf of Mexico or all the way in. We can track Saharan dust all the way up the eastern seaboard, all the way up to here. But in the Carioca Basin off of Venezuela that I'm speaking about, there we get really nice records of how wet or dry or the relative wind speed the northern part of Africa and therefore the northern hemisphere of planet Earth has been over very recent past. 1,000 years, 500 years, 1,000 years, 10,000 years. And when one considers that the last glacial maximum, the last time glaciers here in Boston were about a mile thick or so, that was only 20,000 years ago. And so we can go to places like Carioca and learn a lot about how our planet was set up and how our planet was operating 20,000 years ago.
So I can't remember when the Sahara and I guess a number of these deserts at one time were very rich with flora and fauna and then gradually dried out. You can trace that back through the sediments. You can construct the dates and
with
the conditions.
Absolutely, as best as possible.
Right.
Sure. And of course, the further back in time, the harder it is.
Of course.
But we're getting, with new technical developments and new computational abilities, the ability to date the sediment is getting better and better every year.
Just exactly on that. So here we have a core, right? And you have these layers in it. And the layers are comprised of different kinds of materials. So you analyze those, but now you have to date it. And you've got cores from all over the world. How do you date it? Can you tell us?
Different cores usually get dated by different techniques.
Okay.
And if a core is of a certain young age, there's a lot more techniques we can use compared to cores that might be older. If it's relatively young, we can do carbon-14 dating, which is people are most familiar with that.
Very accurate.
But that's only good to 10, 20, 30,000 years, plus or minus or so. And with material that has abundant organic matter.
Yeah.
As we go further back in time, 500,000 years, 1,000,000 years, 10 million years, we often will use variations in Earth's magnetic field, for example, because some of those very fine-grained minerals that are deposited in the ocean mud will record Earth's magnetic field that was in existence at the time of deposition. And by comparing that to independently documented variations in the North Pole pointing north versus the North Pole pointing south, and the intensity of the magnetic field, that gives us one set of conditions. We also will use radiometric dating, where the decay of uranium to its daughter products, which occurs at a known rate, we can use those techniques to provide a completely different set of age controls. We also look at the evolution of different microfossils, plankton, that are found deposited in the sediment, and we know when certain fossils evolved and then when they died out. And there are people that study a dizzying array of microfossils. So, for example, on a recent cruise that I was just fortunate enough to be on, we were looking at the Sea of Japan and the East Sea, the body of water between Japan and Korea, okay, right there. And on board we had paleomagnetic people looking at the magnetic intensity. We had biostratigraphers looking at the microfossils, and we have samples taken so we can do the radiometric dating. So cobbling together all these different yet independent techniques to date the cores, we come up with a very, very strong, what we call age model, a very strong understanding of the changes and the dates of different horizons in the sediment.
Now, it sounds like that you're able to kind of reinforce your interpretation by having these very different experts, or the different things that you're looking at here, indicators. So it sounds as though you could put together a rather accurate map after that. Is that true today?
Yes. And
with all this very
science
advanced?
is all about testing hypotheses.
Right.
And so, but we do, you know, if we have a paleomagnetic age understanding going down through the layers, usually just because the technique is relatively rapid, we get a good understanding, and then we add in the biostratigraphy, and there's, well, gee, this is inconsistent. How do we resolve this? Because there's only one age at a particular horizon. And then you realize, well, maybe some of the sediment has been remobilized and reworked, or things. But a lot of what we do, and I am not an age dater myself, but a lot of what my colleagues do and what we oversee is the integration of all these different techniques to get at that.
Okay. Before we leave that, I just want to kind of reinforce one thing. You mentioned the magnetic pole shifting, and I'm not sure that people understand that the poles have shifted or do shift, and I don't know if it's a real regular thing, you know, every X years or whatever. Could you just give us a little information about that, because that's such a good clue, I would imagine.
Well, the Earth's magnetic field, which with a handheld compass, the compass points north or points south, depending on where you are, basically acts as a bar magnet. And you can visualize a bar magnet just plunging right through the Earth and coming out in the southern hemisphere. And that magnetic North Pole is located differently from the geographic rotational axis of the North Pole. But it's relatively close, and over long time periods, it's thought that it's essentially an approximation of the rotational axis. And it so happens, for reasons that scientists still don't fully understand, but the Earth's magnetic field does change its orientation. The Earth does not itself doesn't flip, but what is now magnetically north becomes magnetically south, and vice versa. It's thought to be due to the fact that the outer core of the Earth is liquid iron, and the inner core is solid iron and nickel, and that I think I have that correct. And so that's where the magnetic field is orienting, and because it's moving and mobile, it's thought to, and again, this is way out of my field, but this is what is discussed. So these fields, it can switch, and it switches, hundreds of thousands of years time scale. It's not exactly repeated. There's no exact, okay, every 400,000 years, bang, on one Tuesday afternoon, it's going to flip. But there have been repeated time periods of switching throughout Earth history that have been painstakingly documented and painstakingly researched and tested, and we can use these to globally correlate because it's one Earth, it's one magnetic field. That enables us to compare a core taken in this location to another core taken at that different location.
I see, okay. Let's switch off to what you specialize in. You mentioned a little bit ago that you're involved with people from all over the world. There are teams from a lot of different countries. You're spread out in different areas and you're all gathering these cores and stuff. And you do yourself some very interesting work. Could you please tell us about it?
Many of the research expeditions or research cruises with which I'm involved certainly are international. One of the programs that I do a lot of work, the U.S. supports roughly a third or half of the cost. That's through the National Science Foundation, which is supported by taxpayer dollars, and it's basic research into how the Earth and how the oceans work, in essence. This program is the largest marine geology program in the world, and there's about 20 to 25 different countries involved. Various consortia, but Japan, the US, Korea, basically every country in Europe and Australia, New Zealand, and others. So participating in these is a wonderful experience because we get to work with leading scientists from all sorts of different nations. And we take cores and we go out and we look at the layers and we look at climate records. My most recent cruise, we went from Alaska to Busan, South Korea, and our main goal was to look at changes in the Asian climate, and that changes in Asian climate can be documented by the dust patterns coming off of Tibet, the Tibetan Plateau, and also China, northern China, depositing wind-blown dust into the Sea of Japan. And one of the things we're looking at is the development of the East Asian monsoon system.
Yes,
now,
you've done a lot on it.
When we say monsoon, everybody thinks torrential rainfall, which is entirely accurate. But that rainfall is delivering water to the food supply, agriculture. And the East Asian monsoon delivers the water supply to about 20% of the Earth's population. And if you tie the East Asian monsoon into the Indian monsoon and the Indonesian and sort of Vietnam, Thailand area, that's approximately half of the world's population. So understanding the water supply, which is climate, understanding in the past, and not hugely long ago in the past, but 10,000 years ago, 20,000 years ago, 100,000 years ago, what parts of that system were drier than they are now? And was winter time back then colder or drier than winter is now? And was summer drier or colder or wetter than it is now? We call that seasonality. What's the contrast between winter and summer? As we know here, it's quite a large contrast between winter and summer. And that has profound impact over decadal or longer timeframes on the amount of water that's delivered to different areas. So this cruise in the Sea of Japan region, Sea of Japan East Sea region, was looking at the position of the jet stream as it comes across Tibet and China. And is the average position down south, or is the average position a little more up north? To draw a North American analogy, although it's a very different system, but it's sort of like, are most of the storms going to be the jet stream coming through sort of the mid-Atlantic or coming in down from Canada? We all know here that there's a big difference when that weather is coming across the south of the U.S. or if it's coming across the Great Lakes or up through Canada. And over long periods of time, because there's a big difference between weather and climate, short-term, long-term. But you can imagine how if the average position of the jet stream is more northerly or more southerly, you're going to get a very big difference in seasonality, and that's going to dramatically change the delivery of water to a particular area. So in the East Asian monsoon studies that we're doing, we're trying to get a better understanding of what the future may hold. As our planet is globally warming, I hesitate to use the word predict because that's very, very hard to do, but to develop a better understanding of the boundary conditions of how dry could it possibly get, which areas may get wetter, which areas may get drier. Generally, what sort of world are we most likely to be living in, and not thousands of years from now, but 50 years from now, 100 years from now, and again, 20% of the world depends on that water supply. And with the Indian and the Indonesian, that's half of the world. So understanding this monsoon climate is of huge relevance to humanity. And our understanding of it comes from just looking at these mud layers.
That is the most amazing thing. I mean, is there anything, they look at different things to analyze climate as the whole issue of climate change has developed. So there are a lot of different things to look at, a lot of different indicators, but this sounds particularly rich. Are you a little biased if you say that's particularly rich? It just seems like a very accurate source.
No, sure, it takes all types. As we said earlier, when we're talking about different cores and different sedimentations.
Right,
I mean,
understand.
there's a whole other repository, a whole other set of books, which are the ice cores.
Yes, right. But
cores from
again,
Greenland, Greenland or
date.
Antarctica,
Yeah.
and those are layers,
right.
and they trap atmospheric gas, and that's where we have our exquisite understanding of carbon dioxide and temperature change, where there's very clearly the link between carbon dioxide and climate over those time cycles. And I'm jealous of those ice core people in some ways because they get that record.
Right.
But they're jealous of us marine peoples because we get different records as well, and we go back longer in time. And it takes, again, the cobbling together, the different threads of the tapestry. I return to that. The different threads of the tapestry so we can work together the atmosphere, the ocean, the land, put it all together.
Right, and it's another reason, I guess, for having this convergence of fields, that you need many types of deep understanding in order to put it together, and you're still learning a lot. Since you know and have worked so much on this record of climate change and the causes for it, can you give us your analysis of that now in terms of climate change? I still hear, even around here, and Massachusetts is pretty sophisticated in this, but you still hear people saying it's not true. But what's your take?
Well, roughly speaking, more scientists are in consensus agreement that climate change is real and is happening and is due to human behavior. More scientists are in agreement about that than doctors are about the linkage between smoking and lung cancer.
Oh my goodness, yeah.
So I think you'd be pretty hard pressed to walk down the street and find someone who says there's absolutely no relationship between
I
smoking.
don't see it in the science community, right? The problem is not there.
Now, on the other hand, we all have, or many of us might have, an Aunt Matilda or an Uncle Harry who's been smoking like a chimney and is 117 years old and doing just great. But those are statistical anomalies. That doesn't mean, and I don't mean to
don't encourage
cut too close to home or anything like that either. But do we understand cancer? No.
Right. No.
But we understand some key things.
Right.
And that's the situation we're in now. We understand some key things about climate. We understand the carbon dioxide linkage. We understand so much. People like to focus on what we don't understand, and scientists don't like to study what we already know, right? The whole point is to study what we don't know. So we scientists have to do a better job, in my opinion, pointing out what we do know.
Yes.
And not focusing so much on the uncertainty, but focusing on communicating what we know and how we can do better reestablishing what we know. But it really is, again, like cancer, we don't understand everything about climate change, but we understand quite a lot. It's a remarkable consensus.
I was going to say, it seems as though this is one area of science where there may be fewer disputes than in many other areas where there are real differences of opinion, theoretical differences and stuff. But it sounds as though from numerous fields, but certainly from yours, that you have really strong evidence and you can say this is...
In some ways absolutely yes, but I actually think all fields of science roughly have the same amount of agreement or disagreement about
okay.
major theories. I mean, there are a lot of people still studying evolution, but
Yeah.
we know evolution's going on, right? I
Right,
mean, all
right,
this sort of thing.
right.
So there's I don't think our field is any different. What is different is it's been highly politicized.
Yes,
And
I see.
I think one of my frustrations as a scientist particularly has been over the last couple of years, where frankly I think unethical accusations are being made at scientists by people who may or may not be well-meaning about them leveling these accusations at scientists. Some of us feel somewhat persecuted in this way, and that's a strong word, but I'm using it kind of.
You've got a lot of company who feel that way, yes.
And what troubles me is there's a lack of understanding about what science is and how science works. We're not, robots, and we're not pie in the sky in our quest for the great unknown. We're humans. Science is about being objective and about testing hypotheses. And that's what it's all about. But the other thing is people don't understand particularly the American scientific mindset. We Americans love the little guy. We love the person who is going to take down the whole field. That would be fantastic for my career. If I had proof that climate change either wasn't happening or it was happening but it had nothing to do with humanity, all the incentives are for me to publish that. I would be one of the most famous scientists. My papers would get cited. I'd be giving lectures all over the world and all this. All the incentives to me, for me personally as a scientist, are to not go along with consensus. So it's really, and people don't seem to understand that. And then there's always somebody always invariably brings up, well, this is just invented by scientists so they can get more grants.
This is
If you look at the size of the grants and you look at how we're sort of doing compared to some of the other large financial entities who have significant incentives to cast stones, that's not what it's about. But most importantly, we're all people. I would be, as I said, extremely professionally successful if I were to uncover anything, and all the incentives are for me to do that. But I'm sorry, the data do not support that.
right.
Virtually all the data go on to show things. And what's also interesting is that when we don't understand something, like for example, over the last couple of years, it's been thought that the Earth's temperature hasn't been increasing as much. And so, well, and that gets popularized by if you're looking at just a particular time frame, you can say that. But if you look over a longer record of 50 years or so, you can see from your perspective, time going this way, there's ups, there's this, there's that, and you know, overall it's there.
Right,
So
very much
that's
so.
my biggest frustration. But I will also say I have great faith, because at cocktail parties or as an elected official in my town, speaking it with people in the supermarket and so on, more and more people are getting it. And I do think it is one of those situations where, again, back to the smoking and back to the cancer, where Washington, D.C. is out of touch with Americans.
Right. Well,
I absolutely believe that. Washington, D.C. is out of touch on the science of climate change.
Right. And lobbyists are doing a very good job of keeping them out of touch, it sounds like.
That's right.
But that is a peculiar nation also. I guess you have experienced it as that as a scientist, that we have a tremendous scientific community,
We do.
brilliant universities and everything, and yet we have, I believe, the highest percentage of population that still rejects evolution. We haven't made it quite yet to climate change. And then the other part is that people do believe in things that are fundamentally debunked, discredited, and everything else. So the vaccination problem is a very good example of that. And people are routinely fooled by nonsense. So I realize that science community has a long way to go, but it must be very frustrating. I hope that the voters will get busy here and make the government do what it needs to do, for sure.
I think so, but again, I do have faith with the people. And
Yeah.
I think it comes down to education.
Yeah.
And on the one hand, it's an interesting dilemma, as you put it, I think. But on the other hand, what people have access to in terms of information with smartphones and the internet and web and all this sort of thing, I absolutely have faith that overall data and knowledge are going to trump the other incentives that are out there.
Well, they
it
have,
might take longer
yes,
in various things,
right,
but you know,
right.
throughout time, we humans and we Americans have a very good record on figuring things out. It might take a little longer, it might be messier
Right.
due to our form of government,
Right,
but I think the end result will be fine. I just hope it's relatively soon.
Yes,
in the
hope so
particular
too.
field,
Right.
in the particular field. Of
I hope
climate.
so too. Before we go on to your role as a selectman in your community and the problems of your seaside community, is there anything in the work that you have done or that really concentrated on that has been particularly exciting for you, a discovery that you were especially pleased by?
I've been blessed to have a wonderful job that I get paid to study mud and to
Not
go
many
out
people.
and to go out to sea
Yeah.
and do so. There's no one particular thing, to be candid, that I feel particularly proud of or was particularly exciting more than the rest, because they're all way up there.
Yeah.
I will say I've seen some amazing things with this. One of the research trips I went on, again with colleagues from the University of Rhode Island, who were the leaders of it, and I was just one of the team. We went to the center of the South Pacific Ocean. And this is the largest biological desert in the world. It happens to be an ocean, but it has the lowest biological productivity on the planet. And the water there, because there's no plankton floating, essentially no plankton floating in the water, is exceptionally clear. And when I mean clear, imagine if you're on a ferry boat here or in Boston Harbor or something like that, and you can see maybe 10 or 20 feet down on a good day. There, we're able to look, I'm doing the conversion in my head, approximately 250 feet straight down in the water. And because it is so far from land, there's no nutrients, there's no dust delivering nutrients to that part of the world. It has exceptionally slow sedimentation rates, so we're able to look very far back in geological time. We were working on subsea floor biosphere. There's such low organic matter as a food source to those microbes. We've documented that these are probably the slowest turnover biological population on the planet. And it is just mud. And so you're looking at it and it's just mud. But it's kind of cool when you look at it and you realize, wow, that's what's going on in here. Or other parts of the globe I've been to where we've looked at material that's roughly the age of when the dinosaurs were wiped out by the impact 65.5 million years ago. I've actually held that mud in my hand. We were in the Caribbean Sea. So that's a completely different situation. You know, we were down a long distance. We were down 800, 900 meters, so 3,000 feet below the seafloor. And you're holding this mud, and there's no dinosaur femur or anything like that because it's just mud. But you're holding it, and it's like, okay, this is when the dinosaurs were. And then there's this sharp line, and there's a color change. And then above it, that's no dinosaurs. And it's kind of cool when you can just hold that in your hand.
Right.
And it just came up from the seafloor, and you're holding it. It's like, wow, that is a fundamental, boundary in Earth history.
Yes.
And so those sorts of thrills, are why what I do is just cool.
I just think so.
It's just cool.
So you're just overjoyed to go to work most of the time.
Really
I think it's always learning,
really
always learning. You are also an active citizen, and I think that's relatively rare. You know, many scientists go out and speak to the public and stuff, but you're actually elected to do something. Tell us about your community and about being a selectman, and for sure tell us about the particular community and its situation.
Well, I live in Scituate. Scituate. I live in Scituate, which, as many people are aware, is a coastal community south of Boston. And you're probably most familiar with us whenever there's a northeaster that comes in, and
hits
the
you
TV
every time.
channels hit us, and they all come down, and we say it rains cats and dogs and anchormen and women in our little town. But the reason why you see Scituate on TV so much is because its shoreline faces directly northeast, and our latitude is north of the tip of Cape Cod. So we are on the North Atlantic, and we are facing it completely perpendicular. The North Shore, Gloucester, Salem, those areas, they get hit as well, but there the shoreline is parallel.
I
so
see.
They don't get it nearly
Right.
as directly as we
Right.
do, although
I see.
I don't mean to minimize their impacts as well.
Right,
All
right.
So I am a selectman, and this is a small town.
I think it's about the
20,000.
size of this one,
It's
yes.
20,000
Yeah.
winter, 30,000 in the summer, about 13,000 elected, 13,000 voters, registered voters. Selectmen are the executive branch in Massachusetts and a lot of New England and other places. So the executive branch, so there's 5 of us. I'm 1/5 of the president, in other words. The legislative branch, there's no Congress, but instead the legislative branch is town meeting. So that's Norman Rockwell, people
Yes,
standing up at town meeting.
right.
And the judicial branch is taken up by the county and state and sometimes the federal courts. And so we have our 3 modes of government, and I'm involved in one of them. And as a scientist, I did get involved because our community, like many, is facing very real decisions about our water supply, and we're facing very real decisions about climate change. We have many seawalls, and our coastal community gets flooded. We've had some fatalities through the decades, and we've had a lot of homes that get flooded out. So although I am not a coastal geologist, I don't study as my research, as we talked about, movement of sand or anything like that. I do have more than passing knowledge about climate change and what the future may or may not hold in terms of sea level rise and storm intensity and storm frequency. And so I work very hard with my fellow citizens in Scituate to address these concerns. If we just look at seawalls, for one example, to fix all of our seawalls is a $55 million problem. Our entire budget is a little more than that, but we can't do that on our own. Through this position, I've been fortunate recently to be appointed to Governor Patrick's Council on Coastal Erosion, where we're looking at all of Massachusetts shorelines and what we're going to do about it.
Right. Do you find the public receptive to making necessary changes? For example, that you're going to have to change your how close you live to the sea and so forth.
Yes and no, and it's not just proportional to where you live. Scituate, much of it's on the coastline, but by no means all of it. The majority of people do not live on the coastline.
I see.
But we're all involved in, there's a commercial fishing fleet. The harbor is one of perhaps our central location. It's definitely a coastal community.
And when you get hit with the
regardless of where you
northeaster,
live.
you all
That's
get
right.
hit, right?
That's right.
Yeah.
So I do find people receptive because they see the data. And their data, their instruments that they see the data with are their own 2 eyes. And people can recall the blizzard of '78, where Peggotty Beach, which is one of our main areas, was decimated, and many, many homes were lost. And over the last 5 years, with Nemo and all these other storms, Irene, and take your pick, they've seen with their own 2 eyes, and they've lived it. They've been flooded out, or they know friends who are flooded out, or school gets canceled because the high school is used as a shelter, and there are 500 people in that shelter. So it's people are receptive. I've been a selectman for about 8 years now and involved in town government in other ways before that, so roughly 10, 15 years or so. And I've been able to see how people's mindsets are changing. And this is why I'm somewhat optimistic about the future, because I do sense that people, the discussion is no longer, is this happening? The discussion is evolving towards, what are we going to do about it? And that's very reassuring. And people might have differences of opinion about what we want to do about it, but people are now really saying, all right, this is definitely happening here. And let's talk about these different
What are our
things.
options
And that's
given that,
and those are some of the things I'm talking about. You know, people talk a lot about seawalls, and seawalls, as I've said many times, have been, are, and will be an important part of foreshore protection. But they're not the only thing. And in fact, seawalls are eroding our beaches because the energy can't get dissipated and absorbed. They're blocking the supply of sand and so on, but they do protect homes immediately.
Right.
So there's pluses and minuses, but there's long-term issues that we need to address as well, some of which I've written about and so on.
Right. I should point out, we will tie this up now, but for the audience, that he's been very active. Dr. Murray has written in the Boston Globe and so forth, and has communicated especially about the climate change in this area and the effects of these storms and so on. And on the event page for him on our website, there are a list of articles you can access. So I will have to stop there and let you talk to the audience a bit. But Dr. Murray, thank you very much for joining us.
Oh,
thank you.
Thank you. It was a good discussion.
The rate of sedimentation, you said when it happens quickly, you're talking about centimeters per 1,000 years. Is that what you said?
Yes.
Doesn't seem like much.
Well, that's true. Centimeters per 1,000 years might not seem like much because, according to how you and I live our lives, that's not that much. But when we see 20 or 30 centimeters, something like this per 1,000 years, and if it's layered under a microscope, you can see layers. In some cases, you can see winter and you can see summer. So in a period of time that's recorded in this much sediment, for example, under a microscope, you can see winter and you can see summer, and you can almost count each annual year in some locations. Now that's rarity. That's a rarity, but it's not just one location that we can do that.
So you're talking a lot about what biogeochemistry is. I misspoken, but you're talking about what your field's doing a lot today about how it's focused on climate change. Will you see this field expanding to different areas of research in the future, or will it still be focused on climate change?
I think a lot of what we're going to be looking at in the coming decade or so is certainly going to be related to climate change, but one can't study climate change without also studying tectonics, how mountains are built, how volcanoes erupt. A huge area of my research involves looking at the record of volcanism. So when volcanoes erupt in the past, leaves ash deposits out in the ocean, and there's a potential link between volcanism and climate. So I have a whole set of colleagues who are true blue volcanologists that study only how volcanoes erupt. So I collaborate with those people, and there's linkages between tectonics and volcanism and climate. So I think that asking interesting questions and making interesting analyses of the marine sediment that's out there is just going to lead to a whole dizzying array of questions that we can ask about virtually any aspect of Earth's history. And people have been doing this for a long time. It's only relatively recently we've really been able to put more descriptive names on what we do. And it's been very helpful because the next generation of scientists coming up, they don't even think that this is anything unusual at all. Of course you have to study the biology along with the chemistry, along with the geology. How else would you do it? But for quasi-old-timers like myself, we weren't trained that way. It was really unusual for someone to have expertise in 2, let alone 3 fields, but now it's the norm. So I think there's going to be a wide range of studies that people are going to be doing.
Yes, some people have proposed seeding the ocean that's done in a warm or a cold ocean?
So seeding the oceans with iron regarding climate change is not necessarily related to a warmer ocean or a colder ocean. It has been scientifically documented that iron as a nutrient is important, and if we do add it to some areas of the ocean, it will increase the amount of biological productivity because you're just fertilizing the oceans, and that may or may not remove atmospheric carbon dioxide from the atmosphere and put it in the oceans. So it's not so much a warm ocean or a colder ocean necessarily per se, it's which part of the oceans. I'm not advocating that as an approach to solve global warming or anything, but it's one of those areas that we can learn a lot about how the ocean works by doing some very well-constrained studies of what happens if you do put iron into the ocean and so on. It seems that in the past, and this is something I have worked on, it seems that in the past in some important areas, when natural iron is added, the amount of biological productivity does increase. However, the next step, the link to climate, is far less understood. The first step, there's still a lot of questions, but we're getting a pretty good feeling. You add iron, you're going to increase productivity. But taking that next step is quite a big step indeed, which we still need to research.
The areas, you said the areas that experience monsoons comprise about 50% of the world's population, and so it's important that we understand as much as we can about them. But no matter how much we know, is there anything we could do about it? I mean, if the amount of monsoon activity increased or decreased, it seems like there's a whole lot we could do about it.
Well, it's all about preparation. We have road signs when we're driving down a road and there's a sharp curve. And we would probably do okay without that road sign, but it certainly helps. And what we're looking for here are road signs. And we're trying to say, you know, we at this point, we can't say definitively in the year 2100, which might seem like a long time away from now, it's actually not. We can't say definitively that this part's going to get wetter, this part's going to get drier. But the more constraints we can bring to the system, it helps people prepare. And when I mean people, I mean not only the farmers and so on, but governments. Okay, you know, maybe we don't want to invest in a 20-year project to build more dams in this part of whatever it might be if it's thought that that area is going to get drier. You can look at, for example, the populating of Los Angeles. And when they were figuring out how much there was a natural water supply in the early 1900s, purely fortuitously and through no fault of their own because they didn't have the natural records back then, it just so happened that the 10 years that they studied happened to be some of the 10 wettest years on record. So they didn't have the data then, they weren't doing anything knowingly incorrectly, but they didn't have those road signs. And we're trying to build road signs. We're trying to gather the data that there's a curve in the road or there's not a curve in the road, what areas might have it or not. And so the ability to help people plan, help governments plan, is in all likelihood going to help agriculture, help human safety, and so on. Yeah, thank you for the question. Thank you for the question.